All right, well, welcome everyone. Thank you for joining us. My name is Scott Williams. I'm the Research and Education Coordinator for the Wisconsin Energy Institute. If this is your first time in our Sustainable Energy Seminar Series, the Wisconsin Energy Institute is based at the University of Wisconsin-Madison. And our goal is to bring together researchers and educators on campus to support interdisciplinary research collaborations, as well as train the next generation of energy leaders through programs like certificate programs at the collegiate level, as well as improve public understanding of energy issues through public forums and seminars and other outreach opportunities. So this talk today is part of a bi-weekly program called the Sustainable Energy Seminar Series. And the goal of the seminar is to bring together different researchers and experts on campus who study and research different energy challenges and come up with solutions. And this seminar is also part of a class for students in the undergraduate certificate in engineering for energy sustainability, as well as the master's in sustainable systems engineering. And the goal is to really highlight a wide variety of energy challenges and solutions in the way that different disciplines understand and design solutions to these challenges. So today we have Dr. Andrea Strzelec, who is a program director in engineering professional development here at UW-Madison. She is part of the Master's of Engineering and Engine Systems program and teaches graduate courses and short courses in this area. She's a graduate of UW-Madison, getting her PhD in combustion engineering. Before coming to UW, was an assistant professor of mechanical engineering at Mississippi State University and Texas A&M University. So she'll be talking about sort of kind of a high level view of the future of powertrains and the distinctions between electric vehicles, electrified powertrains, and internal combustion engines, and how we can give a more higher level analysis of which technologies are cleaner or dirtier. So welcome, Dr. Strzelec.
Thank you. Thanks. It's really exciting to be here today, and welcome to everyone on the Zoom call. I'm going to today talk about how dirty is in the details when we talk about clean powertrain systems, and really focus on the difference between electric versus electrified. So just to start with, I'll give you an outline for this talk. I want to explain the need and how to compare apples to apples when we're talking about electric versus electrified powertrains. So I'll start with a little brief introduction to tell you who I am anyway. But before we get started, I want to tell you up front that I believe in climate change. I believe CO2 is a problem. And because of that, I have dedicated my career to clean engines. And I'll tell you about that too. I'll give you a little bit of background about how we use energy in transportation, share with you a few engine basics, and then talk about how to evaluate a thermodynamic system. Thermodynamics is the study of energy, its transfers and transformations, and so it's the appropriate science to use for this. And then I want to give you and share some information. I want to challenge some claims that I think are rather incomplete, and show you the options and progress that we have to make transportation clean and sustainable. And just a little spoiler alert, what do I think we should do? I think we need continuous improvement in all areas, and I'll show you why. So I have to start with some acknowledgements because I used some material today from some folks who are even possibly on this call. So Dr. Kelly Senecal of Convergent Science here in Madison, my inspiration and a Badger, he kind of kicked off this defense of the internal combustion engine with a TEDx Madison talk. And he's also the creator of Hug Your Engine, the hashtag, and hugyourengine.com. My advisor, Professor David Foster from Wisconsin, also a Badger, Professor Dennis Desanis, who's now president of University of Delaware, Dr. Graham Conway from Southwest Research, and Dr. Todd Fansler, retired from GM, who works with us here at Wisconsin. I'm really honored to have the opportunity to add my voice to theirs and share this information with you. So thank you, Wisconsin Energy Institute Sustainable Energy Seminar, and thank you, Scott. So what's my objective in being here today to talk to you? Well, in this talk, I want to trash a few false ideas. Number one, electric vehicles are not zero emissions. In fact, there is no such thing. Engine technology has not been stagnant. As I like to say, this is not Rudy's diesel. And a green future does not rely on a single technology. And that's where Kelly says the future is eclectic, right? The future is eclectic. It needs to contain a mix of things. So I want to show you that dirty is in the details because it's all in how you draw the boundary of your system. I'll also show you that engines are continuously getting cleaner through novel combustion strategies and catalysts, my personal specialty area. And so this cartoon encapsulates a lot of what I want to talk about today. You see, there's the guy on top who's driving the diesel car who has tailpipe exhaust, and he feels really dirty because he's driving a diesel. And then the guy on the bottom driving the electric car feels really clean because he has no exhaust coming from the vehicle, but there absolutely is exhaust associated with his motive power. It's just coming from the power plant. So it is separate from the vehicle, but it's still there. This is why there is no such thing as zero. And this is only kind of the tip of the iceberg in that regard. By the way, this is also true for fuel cells. Fuel cells, which generate electricity by by oxidizing hydrogen. Hydrogen combustion only has water as a product, but you had to get the hydrogen somehow. And again, that comes at the price of a lot of power. So why am I talking about this? Well, I am a literal engine hugger. Scott gave you an introduction. I am a triple threat badger. And I want to just toss out a thank you to USDOE for sponsoring my PhD work, which was done at Oak Ridge National Lab. After I finished up, I did postdocs at 2 USDOE labs. And then, as Scott mentioned, I was a professor until I got the call that was a dream of a lifetime to come back here to the University of Wisconsin and run a program all about engines. Who could pass that up? So I'm also, as students in my classes can tell you, really passionate about thermodynamics. Thermodynamics is the study of energy, its transfers and transformations. But the real key to thermodynamic analysis is you have to properly set the boundary for what you want to study. I also don't believe in any kind of bans of technology or demonizing technology. Nothing is all good or all bad. There's no silver bullet that's going to immediately work and clean everything up. I also do believe in engineers, right? It might be a hazard of being one, but I believe that if you give engineers goals and targets, they will be creative and innovative and get you there. And as I said, I believe CO2 emissions are a real problem and they need to be addressed. But I believe that the fastest way to reduce CO2 is by improving all technologies, including the internal combustion engine. So let's talk about some background. This pie chart shows you energy use in the United States by sector. And you can see that transportation accounts for 34% of all energy used, right? Now, here's a note. Fuel economy is not just good for your wallet. Fuel economy also directly relates to CO2 emissions. Hydrocarbon fuels like gasoline and diesel contain hydrogen and carbon, and when they're burned, the products of combustion are CO2 and water. Therefore, the amount of fuel you use is directly related to the amount of CO2 you generate. So fuel economy and CO2 emissions are nearly synonymous. In terms of in use. We'll talk about that in a minute. In transportation, which is my industry, the energy still predominantly comes from fossil fuels. You can see my magnifying glass there is pointing out that 91% of the energy coming into the transportation sector still comes from petroleum. Now, let's talk a little bit of history of engines. The first on-vehicle engine was actually not an internal combustion engine at all. It was a steam engine. We didn't see the first internal combustion engine until roughly almost 40 years later, in about 1807. And then the race to engine technology began. Then we began carbureting. Then we had an internal combustion engine vehicle. Then we had the first diesel engine, fuel injection systems, and then modern fuel injections in the 80s and modern direct injection recently. Engine technology has never been stagnant. We are not using the same engines that were first designed in the early 1800s. And I think that people forget about that. I think when they talk about technology for transportation. They're talking about how batteries are always getting better, and they act like engines aren't. And that's kind of offensive to someone who spends their career as an engine engineer. They sure are. We've come a long way, baby. Okay, so what's the purpose of an internal combustion engine anyway? Well, you want to produce useful work, which in our case is rotating shaft power. And we do that using readily available, stable combustible fuels. They can be liquid like gasoline or diesel, or they can be gas like natural gas or propane. They have a high power, engines have a high power density, which is important for functionality and speed. And they work pretty efficiently at relatively low cost. In some cases, efficiency can be greater than 50%. And if you're thinking 50%, wait a minute, that's not such a good number, I'll show you later on that it actually is, and where and how that has been steadily improving over the years. When we talk about engines, there are two types that we see a lot: spark ignition engines, which are the gasoline engines, so they run off gasoline or alcohols like ethanol, and compression ignition engines, which run off diesel. These both can come in a 2-stroke or 4-stroke variety, and we'll talk about the most common 4-stroke in just a minute. So how does a reciprocating engine produce power? Well, combustion of fuel releases heat in a closed volume. The source of the energy is the chemical bonds in the fuel. The oxygen from air provides the oxidizer, and you have an oxidation of those carbon and hydrogen molecules, which releases a lot of energy. That energy is released in the form of heat, and it's released into the closed volume. As that volume increases, right, because the temperature increases by ideal gas law, what you do is you see an increase in pressure, and that increase in gas pressure is used to push down on a movable piston. Remember, pressure is a force per unit area, and so you have that nice surface area of the piston that the force can push down on. In order to do this well, you want to coordinate your combustion with the piston movement. And I'll tell you that we do those differently, right? How we initiate combustion is different in spark ignited or compression ignited. It's right there in the name. You gotta love engineering nomenclature. We just tell you what it is. And we do have to be a little bit careful to not exceed the physical limits of the engine. So there are certain temperature or stress limits that we need to keep the combustion event in between. This thermodynamic process, combustion is a thermodynamic process, is repeated quickly over and over again, literally in a blink of an eye, during a mechanical cycle. Now, one of the things I spend a lot of time arguing with people on the internet is internal combustion engines do not run on thermodynamic cycles. There is a thermodynamic process that takes place in a mechanical cycle, but that's really key for understanding some of the limitations. So why it's not a thermodynamic cycle is because the closed volume is recharged over and over again with new fuel and air. That does not meet the definition of the cycle. And the engine control system, the ECU or the car's computer, attempts to optimize these processes to make it run well. So here's the 4-stroke cycle, and here's what it looks like. If I tell you that it sucks, squish, bang, blow, you'll probably never forget it. But the strokes are intake. Intake begins by the intake valve is depressed there. You can see that on the left. And when the intake valve is depressed, the air or fuel and air, in the case of a gasoline engine, can be drawn into the cylinder. What happens is that piston moves down and it draws in the air. Intake stops when the piston is all the way at the bottom, the intake valve closes, and then we begin the compression stroke. During compression, both valves are closed, so you have your closed volume. The piston moves up to top dead center, squishing all that air or air and fuel mixture inside. Then we have the power stroke. Now this is begun by the spark in a gasoline engine or by fuel injection in a diesel engine, and I'll tell you a little bit about that in a minute. where we begin the process to release energy and therefore push down on the piston and create that rotating shaft work. Finally, we need to get rid of the spent combustion gases so that we can do the process all again. So we have the exhaust stroke. At this case, the exhaust valve there on the right opens, the piston sweeps up from bottom dead center to top dead center, pushing out all that old gas. And then the exhaust valve closes and boom, we go back to step one for the intake. So that's the mechanical cycle. During gasoline spark ignited combustion, what we have is a case where we mix the air and the fuel before it goes into the cylinder. So we have hopefully a homogeneous mixture. And that's what my golden color of unburned reactants is showing there. Mixture preparation in old days was done by carburation, and that's what you used to tune. So when we talk about taking cars for a tune-up, we meant adjusting your carburetor. Since about the early 90s, most cars have been port fuel injected, meaning the fuel is sprayed into that intake port, so it's mixing with the air as it's being drawn into the cylinder. So you have a nice, hopefully homogeneous mixture of air and fuel that's drawn in and compressed. The load control of the engine is controlled by throttling the intake. The combustion is then initiated by a high energy electrical discharge across the spark gap, right? There's the spark, and it sets off a flame. You can see the orange curve of that kind of sunset shape there, or sun shape there, is the flame front, and the flame will propagate through the unburnt reactants, leaving burned products in their waste. In comparison for diesels, diesels don't have a spark plug. In diesels, air alone is drawn in and compressed. We control the load of a diesel by how much fuel we inject in. So only air is drawn in and compressed, and then the power stroke in diesel happens when you begin your fuel injection and have the combustion that is ignited by that hot compressed air to initiate combustion in a process called autoignition. So the heterogeneous mixture in the cylinders, because the air and the fuel are mixing right there, leads to a wide range of mixture concentrations over which these reactions occur. And therefore, emissions, exhaust emissions, are a much more significant issue for diesel engines than they are for gasoline. However, they can be cleaned up with exhaust aftertreatment catalysts. And I know, I literally wrote the book on it. It's right back there. Oops. But when we talk about engines, and especially when we're talking about CO2, right? I said that CO2 and fuel economy are related. Fuel economy standards are not enough. The targeted fuel economy standards for 2020 were insufficient to level off our CO2 levels because we see an increase in vehicle miles traveled in general. True, the pandemic has slowed that down, but there are also more countries coming online as having vehicles. So our CO2 emissions in developing nations are increasing. And then also, even though you might have cars that are developed with higher and higher mile per gallon ratings, the issue is people don't buy a new car every year. And so it takes a long time to penetrate the vehicle fleet in order to get that average fuel economy higher. So CAFE, which is the corporate average fuel economy standard, is actually why the PT Cruiser is considered to be a light duty truck. That says that for a certain size class of vehicle, the average fuel economy has to be a particular level. So for example, you can take something like the PT Cruiser and make it fit the definition of a light duty truck and average its much higher fuel economy numbers in with maybe your light duty pickups, which don't get quite as much fuel economy, and keep those numbers average. So now, here's the question. When did engines become such bad guys anyway? When did they become the villains? Well, unfortunately, I can point to the answer in this, and that's really the Dieselgate scandal. If you don't know what that is, that's a scandal involving 11 million vehicles between model years 2009 and 2015 that were intentionally programmed not to meet emission standards. Note, the vehicles absolutely could be clean. They had all the after treatment they needed to be clean. But Volkswagen prioritized the fuel economy of the vehicle over meeting emissions. And so unless the vehicle was being tested, they didn't run the after treatment. The result of this was a couple things. Big fines. I think some of the largest EPA has ever doled out, and jail time for some of the Volkswagen executives. It also resulted in lots and lots of claims of the end of internal combustion engines and the beginning of what I'm going to call the EV hype. And by the end of this talk, I hope you understand why I say that. So you can see The Economist there, which shows the engine is roadkill. And then the BMW headquarters, which was very famously built to look like a 4-cylinder engine, turned into batteries with some lights and with the saying, "The future is electric," which I'm pretty sure inspired Dr. Senecal to change it to "The future is eclectic." Now, let's talk about the science. So when we talk about thermodynamics, it's really important to define your system. That's whatever it is you want to study. The first thing that you do for energy analysis is pick what that is. And this is the most important step in thermodynamic problem solving. You might think that sounds too simple, but it's totally true. Everything that's not in the system is the surroundings. This is going to be important later on. So everything not in the system is the surroundings, and the boundary is what we use to distinguish the system from the surroundings. So we have to really consider the system that we are considering when we're doing a direct apples to apples comparison. If we're only looking at tailpipe emissions, are we actually comparing the correct systems? So from our standpoint, we all live in the same system, planet Earth. And as we continue to fill it up with CO2, we can play whatever games we want to play with choosing the systems on the right, but the system on the left is going to suffer for it. So you can make the math work out for you if you want, but it's all showing up in the planet Earth system anyway. So I'm going to tell you right now, to do a proper comparison of efficiencies and emissions of these vehicles, you can't cherry pick the system. One vehicle is considering the source energy and the other isn't. My Tesla there has no CO2 emissions at the tailpipe. Actually, it doesn't even have a tailpipe. Whereas the Ford Edge has CO2 emissions at the tailpipe. But the Ford Edge is considering the fuel that's inside the vehicle being converted to power, and the Tesla is not, because it doesn't have the power conversion on, or the energy conversion to power on board. It only has an energy storage device in the battery. So, is it fair to say that the Tesla is clean and the engine is dirty? Not so much. If we make a fair comparison, in the state of Wisconsin, most of our power comes from coal-fired power plants. So there, I fixed it. Look at that nice coal power plant that's in the picture with the Tesla. That's the correct system to compare directly to the Ford Edge, right? You have to consider the source energy for both cars. Electricity isn't naturally occurring. Making it generates CO2, and you're not making it on board in the vehicle, you're storing that electrical energy on board in the battery and then using it in the electric drive motor. Right now in the United States, 70%, actually quite a bit more like 75%, still comes from fossil fuels. Now, big exceptions to this. If you're watching us today from Norway or Iceland, congratulations. Your electricity is in fact renewable. Norway has nearly 98% renewable energy, and Iceland is 100% renewable on steam. So then in that case, perfectly clean. And you can see that Wired magazine shows you sort of the makeup of the kind of power being used to charge these cars in the various markets. In this case, when we consider the power plant, the Tesla is no longer so clean and the Ford is no longer so dirty. So that's just the tip of the iceberg. If you're thinking to yourself already, but wait, engine hugger girl, I am going to use only the most perfectly clean nuclear energy or solar energy or wind energy. That's not the whole story. it's not only the in-use phase of the vehicle. So when we talk about this analysis, it's cheating to just look at the vehicle analysis. Vehicle analysis, also sometimes called wells to wheels analysis, only considers the emissions produced during the usage of the vehicle. But that's not the whole story. Life cycle analysis, sometimes called cradle to grave, considers the emissions produced by extracting and fabricating the materials that make up the vehicle, transporting those materials to the factory, assembling it and all that, as well as that usage phase. So in this case, wells to wheels is looking at that top line where we're just looking at primary fuel production through the refining, to the distribution, to the fuel station, to the vehicle use. But that bottom line there is also important. By the way, each time we transfer energy, we lose some of it. Real processes have losses associated with them. There's things like friction in the engine, or electrical resistance in electrical lines. Every time we handle energy, to make it simpler, we lose some of it. So for an engine, we put the energy directly into the system in the form of fuel, where it is directly converted via combustion to power. We do lose some of that energy in the combustion process, and you can come take my thermodynamics class and learn all about that if you want. For a battery electric vehicle, to put the energy into the system, we first have to turn the fuel, still often done via combustion if we're talking about coal or fossil fuels, into electricity. We need to transfer the energy via power lines. We need to transfer and chemically store the energy in a battery, and then we need to withdraw the energy from the battery to power the electric drive motor. So that sets up this comparison. If we only consider the tank to wheels on the right in kind of the teal color, you'll see some numbers that are often quoted. Oh, electric vehicles are 80% efficient, and gasoline vehicles are only about 30% efficient. Well, by the way, these numbers are maybe a little bit off. I think gasoline, especially with gasoline direct injection, is up around 32 to 35%. But still, that looks pretty bad, right? Now, however, if you consider the entire analysis here and get the power or get the energy to the vehicle too, well, now we start adding in the well to tank portion, meaning the power generation, the transmission, the battery charging, or the refinery and transportation on the vehicle side. And you can see now the efficiencies flip. And we're about 83% efficient when you're talking about the conversion of oil into something we can put in the vehicle, and about 30% efficient. A Rankine cycle power plant's roughly 33 to 35% efficient. And overall, remember, efficiencies are multiplicative. You end up with somewhere around 24% efficient on both. So it's not exactly correct to only look at the right-hand side of this slide. Now, by the way, fun fact about Wisconsin winter weather, especially as we're headed towards yet another snowstorm. So this was DOE Fact of the Week from just a couple weeks ago, and it's showing you a comparison of fuel economy losses that happen by vehicle type. So the comparison is a Wisconsin summer day where we're driving a gasoline vehicle in the city at about 77 degrees, and that's our 100%. That same gasoline vehicle doing that same city driving when it's 20 degrees Fahrenheit, like today, is 15% less efficient than it was in the summer. And then when you look at hybrid vehicles, they take a bigger hit, 30 to 34% less efficient. And fully battery electric vehicles, like a Tesla, takes a 40% fuel economy hit. So actual fuel economy, of course, will vary by vehicle, driving condition, many other factors. But you can look up the data, this fuel economy in cold weather. I'm sure if you Google DOE Fact of the Week, you can see all the data that goes to support this. So notice that these efficiency numbers are not only impacted, like what we said, but they're also impacted by ambient conditions. And batteries like cold even less than my parents who moved to Florida do. However, this is still not the whole picture. What about the manufacturing? And this, my friends who said before, but I'm only going to use green energy sources like nuclear or solar. Here's where you need to pay attention, because this is what's saying that's only part of it. So let's talk about the cradle to grave. When we talk about cradle to grave, we're including the manufacturing sources of CO2. And let me tell you, having a big battery means that you're starting with a heck of a lot more CO2 before you even drive 1 mile with the vehicle. So let's look at the BMW 320d as our comparison vehicle. It runs a diesel engine, my favorite kind. It generates about 109 grams per kilometer while you're driving. So that's the number that we're going to compare to. We're going to compare making these batteries to driving this vehicle. The CO2 that we make from just making the engine is like driving that beautiful vehicle 950 miles. Now, moving on to the Nissan Leaf. Nissan Leaf is a battery electric vehicle. It has a 150-mile range, and it achieves that with a 40 kilowatt hour battery. The battery production generates 4,800 kilograms of CO2, which means before you have even driven that Nissan Leaf 1 mile, you've generated enough CO2 to have been driving that 320D for 26,600 miles. And the answer gets even larger as we talk about a bigger battery. So when we look at the Tesla Model S, it has anywhere from a 325, 350 mile range. It achieves that by using a 100 kilowatt hour battery, so bigger battery. Bigger battery means we generate about 1,200 kilograms of CO2 from producing that battery. So before you've even driven the Tesla Mile 1, you've generated enough CO2 like from driving that BMW 70,000 miles just from the production of the battery. So thank you, Kelly, for that data. All of this is using 120 kilograms of CO2 per kilowatt hour. That's about middle of the range. You can see numbers that are bigger or smaller, but that's about the average. So the bigger the battery, the more CO2 you generate in creating it. So let's take a look at this plot from Graham Conway at Southwest Research and the amount of CO2 produced over the life of the vehicle. You see that my conventional vehicle, AKA IC engine vehicle, starts with the lowest amount, which we just talked about with the BMW. The smaller electric vehicle, like the Leaf, starts in the middle, and the full larger battery electric vehicle starts with the most. Even though the slope of the blue line is the steepest, it takes about roughly 90,000 miles of driving before we make as much CO2 as driving the electric vehicle with the 125 mile range. And also, at nearly even 180,000 miles, we still haven't caught up to the electric vehicle because of how much energy or CO2 it makes just to create the battery. So this has the lowest slope, still has a slope, by the way. If it were truly zero, it'd be a flat line. It's not. The power had to come from somewhere. In the US, it's coming from fossil fuels. Therefore, there's still a slope to that line. Okay. But now you're maybe thinking, but engines are old technologies and batteries are the future. I warned you about that up front. Actually, electric vehicle sales peaked in 1912 in terms of the total vehicle sales percentage. So the first EVs showed up in the 1850s. Look at this Waverly. It's an electric, right? Look, you even had electric taxis in New York City in the 1890s. That's not a new phenomenon. But they were nearly extinct by the 1920s for many of the same reasons we face today. Battery energy storage capacity, the so-called range anxiety, limited charging stations. We don't have the infrastructure for charging batteries, and competition with the internal combustion engine. And if you're saying, but batteries are always getting better and we're moving towards renewables for electricity, well, engines have always been improving too. And this is a beautiful slide by Dr. Todd Fansler that shows some of the really cool, advancements we've made on the engine side. Variable valve actuation, EGR, high pressure direct fuel injection, my beloved particle filters, lean NOx after treatment like SCR or LNT, and then really awesome control systems that make it all work well together. And these things are getting results. There's a number of DOE programs out there, like the Super Truck program, which has nearly doubled the fuel economy of semi trucks that are driving all our wonderful Amazon packages around. And the Co-Optima program, which is saying, hey, let's make better fuels and better engines together and faster. And if you look at this cute little graphic down here in the bottom corner, you see that fuel economy, right, miles per gallon, has been increasing, and that's really notable because cars have gotten a heck of a lot heavier due to safety systems, and we all love those parasitic electronics like heated seats or, you know, all these bells and whistles that we have in the vehicle. And those are all things competing with your motive power for energy. The other thing is sustainable fuels exist as well. Biofuels are renewable. Biofuels are things that are derived from biomass, plant matter like trees, grasses, ag residues, algae. And there's a huge range of options that you can make them into: biodiesel, bioethanol, bioreformates like Virent right here in town, biomethanol, biogas, lots of bio. And you see, then you're setting up for participating in a carbon recycling loop instead of releasing all that chained carbon that was in the petrochemicals. And big oil is already greening up their refineries. They're using existing refinery infrastructure to make these renewable fuels. There's also this really cool thing called net zero carbon e-fuels, where we're using electricity to produce liquid fuels from captured CO2. So it allows you to be carbon neutral or even net carbon zero because you're capturing CO2 from the air, making it into fuel, and re-releasing it as you use the vehicle. Okay. So this is all confusing. One's better, one's not better. I'm confused. So what should we do if we really want to go green? Hybridize. So there's many levels of vehicle electrification. An electrified car isn't necessarily electric, but an electric car is electrified. A battery electric vehicle is 100% electric. If a car has an exhaust at all, it is not electric. Pretty much battery electric vehicles, fully electric, everything else is some level of hybridization. And we have lots of levels of hybridization. And what does it mean to be electrified? Well, it means using electric power beyond just the basic accessories like starter lights, ignition, which is what your 12-volt battery is in your conventional vehicle. But it's inclusive of vehicles using a wide level of power beyond that. Micro hybrids, things like start-stop technology. If you have that in your car, you're a hybrid. Regenerative braking is a level of hybridization. Mild hybrids, so maybe getting some of that torque assistance now. Full hybrids, it means now you're incorporating in some electric driving as well as battery charging from the internal combustion engine. Then we have plug-in hybrids, where you have both the engine and the electric drive motor, but you charge the battery from the grid power. And then an extended range electric vehicle means that we have an engine on board, but it's only used to charge the battery or run the electric drive motor. It never powers the powertrain directly. But that big list of things that are not battery electric vehicles, that are electrified vehicles, all of them still include an internal combustion engine. So, brief recap: battery electric vehicles powered by an electric motor. The battery stores electrical energy that powers the motor. The battery is charged by plugging into some outside electric power source, you know, those magical wall outlets, and there is no tailpipe emissions. The driving range can be up to 400 miles per charge. They say there's a lot of variance due to what model of vehicle, what trip, drive cycle, and environmental conditions like Wisconsin winter. Hybrid electric vehicles use both an electric motor and an internal combustion engine. Lots of configurations exist, and they all have different capabilities. Some of the types of hybrids we've talked about are mild, strong, and plug-in. Now, plug-in means that you employ the plug-in feature to get the electricity from the grid. It uses that grid energy to propel the vehicle, and it loses battery charge during driving. Hybridization increases fuel efficiency. It allows us to downsize the internal combustion engine because the batteries make up for that extra power. It allows us to run that engine at its optimal settings. We can use regenerative braking to reuse the previously lost energy due to friction. We can shut off the engine at idle. Like we said, there are several levels of electrification, and we can have both series and parallel arrangements. Both have their advantages and disadvantages. In general, a series hybrid is more efficient, but less powerful than a parallel hybrid. In the interest of time, I'm going to just go through quickly and show you what these look like. The students in the class can study these slides later. But in order to make a fair comparison of the hybrids against both parents, we have some of Graham's plots again. And now we're looking at the CO2 produced over the life of the vehicle. Note that this hybrid green line here is lower than either parent. Notice that the CO2 produced over the life of the vehicle, the hybrid doesn't even catch up to the fully electric vehicle till about 450,000 miles. Hybrids produce more emissions than the engine in terms of the manufacturing phase, because there is the battery there, but way less than battery electric vehicles because they have a smaller battery. So they start nearly the same. Making and using a hybrid in the US produces, in the US, I am talking about US power and where it comes from, produces less CO2 emissions than a conventional IC engine powered car or a battery electric vehicle. It's just undeniable here. So hybrids, better than either extreme. Hybrids are electrified, meaning they have both electric and an internal combustion engine. And that means that traditional internal combustion engines are not going to disappear overnight. They're going to keep continuously improving. There is a future for them. We need them. We need to keep working on them. And that's what the folks at the Engine Research Center work on here. So to steal a line or slightly misquote a line from Mark Twain, thanks Todd for this, reports of the death of the internal combustion engine have been greatly exaggerated. So let's wrap it up now so I can take some of your exciting questions. The future of transportation needs to be diverse. It needs to be including all of these things: spark ignition engines, compression ignition engines, gas and diesel fuel, alternative fuels, advanced engines, hybrid powertrains, fuel cells, hydrogen, electrified powertrains. All of these things are the answer, not just one. There's no silver bullet. No one of these is the right answer. Which one of them is best for the system depends on a number of things. I've made a compelling case, I hope you think, for hybrids in the United States. But again, if you're in Norway or in Iceland, then maybe you want to go with just the electric powertrains, right? The answer depends on a lot of things. And anyone who's been telling you there is this X answer is giving you an incomplete story. There's a lot of technology enablers for efficient powertrains. There's energy storage like batteries or even hydraulic accumulators. We have clean combustion strategies, fuel cells, alternative fuels, aftertreatment. All these things lead us to hybrid propulsion options that are cleaner than either of the extremes. There is no silver bullet in this situation. And in fact, if anything, this really shows the power of and. Dramatic reduction in fuel consumption and vehicle emissions is going to come from efficient energy conversion and next generation biofuels and vehicle electrification and lightweighting of our structures so that our energy going into the vehicle gets us further. But it has to be guided by a holistic life cycle analysis and an optimized framework. You can't just pick and choose the system you want to look at and not consider what you're including or not including in the comparison. So as Kelly says, the future is eclectic. It needs to be eclectic. It needs to be about and. So what did we hopefully learn in this talk? Well, number one, no such thing as a zero emissions vehicle. You have to draw the system boundary to compare apples to apples, which means including the energy source, because that's where the emissions get generated. So you can have your tailpipe emissions or your distributed emissions, but they're both still there. Manufacturing also generates emissions, and a lot more for batteries than engines. We can't ignore that. That's a really big deal. And both engines and batteries are old tech, and both of them are continuously improving. Thank you, engineers. Um, Hopefully you also realize we shouldn't pick winners in advance. We shouldn't use political policy to choose a technology. We should choose the targets. We should use political policy to choose the targets, efficiency, emissions, and let the engineers go to work and make it happen. Policymakers shouldn't try to guess what the level of creativity of engineers. Let the engineers get there however it's going to happen. Thermodynamics is not political. It just is. And because of that, we should be working on improving all technologies. And then hopefully the last thing you see is in the US, hybrids are better than either extreme. Higher efficiency, lower emissions without the range anxiety. It's the best near-term solution and the fastest way to go green. So just a couple thanks real quick. I stand on the shoulders of giants who've led the way in defending the internal combustion engine. So I thank them. And I only got to this point with the guidance of my advising team at Wisconsin and Oak Ridge, my funding sponsors, Gurpreet Singh and Ken Howden from DOE, my parents, Mike and Rosemary Strzelec, possibly joining us via Zoom. And I am really honored to have this opportunity to add my voice here today. Thank you so much. And I will be very happy to take your questions. Remember, the fastest, greenest solution, hybrids. The future is eclectic.
Thank you so much, Andrea. We've gotten a lot of great questions coming in through the Q&A box, and I'm sorry, I don't think we'll be able to have time to address them all. One thing, there's a few different questions related to sort of the scarcity of materials and comparison with their either battery materials or fuel cells versus after treatment. Do you have any kind of thoughts or comments on that?
Sure. I mean, there's and actually, let me jump out of slideshow mode for a quick second, just so that I can type my email on the screen here someplace. And then anyone who didn't get their question answered today can feel free to send me an email. I will be happy to answer that. Oops. There you go. So actually, you know, one thing I didn't talk about today is, in fact, some of the battery materials, things like lithium, right? Lithium, which we use in everything from my cell phone battery to the car batteries, and we use it in medicine, we use it in a lot of fields. The majority of lithium, when you talk about mining rights, is owned by China. There are geopolitical issues involved with some of those materials. When we look at other materials used in batteries like cobalt, cobalt is mined in the vast majority by child slave labor in the Democratic Republic of Congo. So there's a lot of sociological issues associated with batteries as well, right? If you go to subsea mining, by the way, which is super expensive, but then the United States becomes the world's largest owner of lithium. So when we get really desperate, I guess we'll go there. Scarcity of materials is true in any field. We just talked about lithium. When you look at after treatment, the rare earth metals, the platinum group metals, are really expensive and rare. And that's another thing that we're working on, is how do we get away from using those because they are limited in supply. I think there's a lot, I can only speak to the emissions part of it because that's what I work on. There's been a lot of work in looking at alternative catalysts. Can we use silver instead of platinum, or how do we get away from rhodium, which is $13,000 a troy ounce? That's about 32 grams. Super expensive stuff. Those are problems that face both fields. So if you were looking for the scarcity of materials to help solve this debate, it's not going to do it. It's there in both fields, and you know, that's why we got to keep working.
I'm gonna go down to David because he has a similar question that I have. What are the main reasons for such a high CO2 produced during battery production, and how likely is improvement to be made there? And so I guess I might add to that, you know, I think there's a lot of talk about cleaning up electricity. It might be a little easier to do nearer term, you know, if we're kind of thinking big picture. So if we have very clean electricity, does that also then affect the manufacturing emissions of batteries?
No, not entirely. Remember, when we talk about the manufacturing of batteries, we're talking about mining for lithium, right? You got to get all the raw materials. So they use these giant Caterpillar mining trucks, right, to go down and bore in and then it has to be cleaned up and transferred and all that. So it's not just an electric power issue. There's a lot of emissions associated with the whole supply chain. That's one of the reasons that number gets so high. Um, I mean, I think cleaner energy will help, but again, it's not the whole story.
Let's, someone, Senthil has a question about e-fuels. Would simply running renewable hydrogen combustion engines or fuel cells be more efficient than converting to fuels? And what does its LCA look like?
So e-fuels are pretty new. E-fuels are highly energy intensive, right? It takes a lot of energy to capture the CO2 and catalytically upgrade it into liquid hydrocarbons. So that's still a very energy intensive process, which again, going more renewable in that would help. How do they compare in terms of efficiency and direct use in an engine? I think they've been shown to be on par with using petroleum hydrocarbons. Hydrogen starts to get into some of the issues again of making it. How do you make it, and you know, how do you store it? And so that's also a very energy intensive process. So there's no one answer on this. I will say that I know there's a really great paper coming out later this spring that attempts to answer a lot of these questions from Kelly Senecal and Felix Leach and Graham Conway. And so I think once that comes out, we'll see some more of these comparisons and how all the parts come into play in this. I mean, one of the biggest problems is this is a very complicated system to analyze and analyze correctly. And in every case, every parameter you put into your model to decide what something is better or worse, right? There's a sensitivity analysis that goes with it. There's trade-offs to it. And so it's really complicated to get the data that you need to make these decisions, and then also to know how much does any one parameter weight affect the overall model. I think that's what makes it really hard. And I think there's a lot of publications out there, especially in the popular press, that don't bother to tell you what the underlying assumptions are that they made to get to their answer. Even some scientific papers are leaving that out or not acknowledging how sensitive one particular assumption they made is. So I think it's a complicated problem, which is why we have to keep working on the whole thing in order to make it better. We can't just choose, we can't crown one technology the king, the winner, and just go from there. We have to keep making everything better, because sometimes something you learn in one field pays off in another. And I think it's really important to keep striving for better.
Kind of a two-part question here. One is based on the sometimes subjective underlying assumptions and LCAs, how do you see LCA being used in legislation or certification? And then the second part is, for each use case, what do you see as the best fit for battery electric vehicles?
So for legislation, I mean, honestly, just the idea that policymakers are considering the full life cycle would be really exciting to me. I think one thing that happens a lot is they are under a lot of misconceptions about things. For example, people will often say like, oh, but engines are limited by Carnot efficiency. No, they're not. Not a thermodynamic cycle. Because of that, not limited by Carnot efficiency. Limited by the second law? Yes, not Carnot. I think the policymakers need to listen to the scientists and engineers, and they need to learn to ask good questions. They need to learn to get the full story and ask what the trade-offs are and ask what these numbers are assuming. Don't just accept the data handed to you and run with that, because I think we've seen a lot of that. I tell people all the time, I think thermodynamics, and especially the second law of thermodynamics, is probably the most important piece of science out there. And I, I proselytize about it because I really think it can help you make good decisions. So doing life cycle analysis is hard, but it doesn't mean that we shouldn't do it. And we have things like the National Academy of Engineers or National Academy of Science. There are people who are capable of doing this analysis, that we really ought to be charging with this to help us understand it without any political bias, right? And then what do I think is the best case scenario for batteries? Was that
For
the
use
second part of
case,
the
best
question?
use cases?
Best use cases. Well, I mean, I think the best use case is in hybrids. I think the best use case is in hybrids. It gives you all the options and really works out in the end. I mean, we saw Graham's plots, right? You can go a long ways with a hybrid because you're using a smaller battery. If we can clean up the emissions associated with battery production, and if we can, I mean, you see how I'm going to have to start like piling on the if and if and if I would have won the Powerball last night or whatever. Then I think that the range issue with batteries is not something that any of those ifs are going to address. So then maybe small routes, mail trucks, local delivery trucks, garbage trucks, anything that's going to go back to a home base, buses, right, every night, where they know exactly how much they're going to drive and then can go charge for long periods of time. Because we didn't even talk about that, right? I mean, one fun calculation for your students to do, Scott, is to calculate how much energy you put into your gas tank in the 3 minutes it takes to fill up the tank, right? And then just realize that amount of energy was transferred in minutes. And even the fastest fast charging you can do still takes an hour. So there's a lot of issues that just greening up the grid won't solve, right? That still make the answer to be both.
Great, thanks. And then might have time for one or two more questions. One from Todd. Isn't comparative simplicity one of the attractions of battery electric vehicles for auto manufacturers relative to the IC engines, or especially hybrids, which have all the complexity of both systems?
Well, Todd, that depends on who you ask. I am well known to be absolutely terrified of electricity, and actually, there's going to be a really cool elective class in Introduction to Electric Drive Motors for traction applications. It's an EPD 690 8-week class running this spring. I really look forward to sitting in on that and learning more about it. Because I'm terrified of all things electrical, I find the nice mechanical internal combustion engine to be something I can, go and work on. I think it all just depends. I don't know if I can say it's simple. I don't know that control systems for battery electric vehicles are any easier than control systems for internal combustion engines. So I think it depends on your area, and maybe after I sit through our electric motor class, I'll have some different thoughts on that. But I mean, you can't deny, right, that there are engines, there are Model Ts, right, that have engines in them that still run now. We don't have any modern or electric motors like that I'm aware of anyway. I mean, they may be out there, that we can compare and say the longevity of this stuff, or how many miles it'll go for and all that. So time will tell.
I think maybe we'll ask one last question, more of a kind of a general public question, see if I can pull up the question. What do you think the best approach is to demonstrating these differences to the general public who aren't going to take the time to understand life cycle assessment, et cetera?
Well, I'm giving a version of this talk on PBS Wisconsin, so I think getting the word out there, and telling people, right? I mean, that's why I talk about people who have led the defense of the internal combustion engine. Kelly did a TEDx Madison talk. Graham Conway did a TEDx San Antonio talk. We have to advocate, right? We can't just accept that batteries, are the chosen winner, and it's not necessarily the right answer in terms of that analysis. So I think we have to go out there and educate energy policy, be energy advocates. We need to give talks like this. We need to talk to students. We need to give people the information to at least start asking the questions, right? Kelly tells a great story about how, when in his version of this talk, when he talked about, oh, electricity comes from somewhere, people came up to him afterwards and felt like they had been lied to, thinking that their Tesla was so clean. So I think it's on us, as scientists, as researchers, as people who have this education, to share it, right? So that so we can get the word out there, and to lobby our politicians and policymakers.
Great, thanks so much. And I've shared your email address again in the chat if I
Thanks.
didn't get to your question. So thank you all for joining us. Really great questions all around and great presentation from Dr. Strzelec. Thank you so much for taking your time to speak with us today.
Scott, if you can, if there's some way that we can capture those questions,
Yep,
and
I will. I should be able to have a transcript of all those questions, and I can share those with you as well.
cool,
Um,
cool.
and
I'll work
then
on, trying to answer them via LinkedIn or something, just to help get it out there. Thank you so much. Thanks for having me today.
Yep, and this session is being recorded. So if you missed, or if you want to share it with friends and colleagues, I'll send the link to everyone who registered for today's session, and we'll also post it on the Wisconsin Energy Institute website in the Sustainable Energy Seminar Series. So thanks all for joining us today, and hope to see you again. We'll be here again in 2 weeks, and thanks again. Talk to you soon.
Thank you.